questions.
Yes, I'm ready for your questions.
Okay, so I wanted to start with what gives subatomic particles their charge?
Okay, so that is a bit of a complicated question. So I'm not a particle physicist, but if we look at our normal subatomic particles, we have the proton, neutron, electron. So protons, neutrons, and electrons are made up of smaller particles called quarks. They are up quarks, charm quarks, strange quarks, and down quarks. So depending on the combination of those quarks, you will get a net positive charge, a net negative charge, and a neutral charge. And then when the molecule starts binding, depending on how many protons, neutrons, and electrons they have, will determine the charge of that particle, but it all comes down to its composition of quarks. So for our aims and purposes, electron is negative, a proton is positive, and then those particles also have mirror reflections that's negative. So for an electron, you get a positron. Does that answer it a little bit?
Yes, sir.
So it
And
all depends on the composition of the quarks inside of them.
yes, sir. And so I've heard that these subatomic particles, like for example, an electron, it also has like uh like there's a similar type of particle like that, but then it's heavier, right?
Heavier, so you are speaking of a neutrino.
N- So I'm not sure exactly like what it is. So, but then like I've heard that like under
Are you speaking about like Mr. Van der Berg suggesting in chat muons?
yes, and they were saying that on the standard model, like everything, like basically like the subatomic particles have a cousin that is similar to them, but they are much more heavier than they are, and like they don't necessarily interact with one another, but then like they're very similar to how they're made. Not made, but like how they are. They're just heavier.
Yes, that is interesting. I've read the articles of CERN where they are talking about muons and discovery of muons. I'm not that familiar with it, so I cannot answer your question about muons, but I will read up about it.
Okay, so maybe you'll be able to answer this one.
Yes. So let me just investigate it a little bit.
Yes, sir. So how sure are we that everything is sort of moving away from us in terms of um we say that the universe is expanding. So why do we come up to that conclusion instead of like because like the universe is so big, so why can't it be some complicated motion that we haven't necessarily thought of?
So we know the universe is expanding by looking basically at the Doppler effect of everything around us. So in astronomy terms, when we make use of the Doppler effect, it's redshifted and blue shifted like we did in a previous lecture. So it's not really red and blue, but it's just a way for us to represent itself. So when we look at a map of the Doppler shifts of everything around us, when things are moving away from us, it will be redshifted. If they're moving towards us, it will be blue shifted. So the majority of everything we can see in the universe around us are red shifted, meaning it is moving away. And that falls into the expanding universe, because if you have expanding universe, everything is expanding. So you can think about it, if you have a balloon and you have a Sharpie or Cokie and you make dots on that balloon, and you draw the dots on a balloon without blowing up the balloon first, and you'll see the dots are very close to one another. And then you start blowing up the balloon, and as the balloon increases in size, you will see those dots are moving away from one another. And that is the principle the universe is expanding with.
But then, so here is like an example. So I don't know, maybe if uh I'm thinking about it in the wrong way. But then, like, so you see, the Milky Way, right? We're not necessarily by the spiral arms of the Milky Way. We like sort of like in between. Am I correct?
We are close to one of the spiral arms of the Milky Way.
Yes, but then we're not in it. So then, for example, so like we know that these spiral arms, so they sort of move in like waves, if I'm correct. They sort of move in like waves. And so like can't you sort of say like um majority, right? Majority of the galaxies that we see around us are sort of like moving past us in a way, but like we also moving like in the opposite direction compared to the rest of the universe.
That's a difficult question to answer in that way, because the Milky Way galaxy is moving. We are moving inside the Milky Way galaxies, and different galaxies are also moving. But in a couple of lectures, we're going to discuss formation of galaxies and how galaxies move. And I think then it will provide a clearer image of your question.
Yes, sir.
Awesome. Mr. Greatman, I see you have raised your hand.
Yes, sir. So I wanted to ask about, I had this whole thing that apparently the universe we're seeing today isn't the universe at this present time. It is the universe a couple of years ago, because light travels a distance, and in order for it to reach us here on Earth, it uh, reaches us at a certain amount of time. So, for example, when I'm seeing the screen of my laptop now, I'm seeing it a couple of seconds ago, not at the present time. So, with our planet, it's a longer distance, hence it's much more time. So, the universe we're seeing today ain't the present universe.
Yes, that is completely true. So when we think about it, it takes the sun light 8 minutes to reach Earth. So let's, for purely example, if the sun would completely disappear, it will take us 8 minutes to notice it, because the sunlight that received us now left the sun 8 minutes ago. Going a bit further away, the closest star to us besides our own sun is Alpha Centauri, and that's about 4.25 light years away. So if something will happen to Alpha Centauri, we will only notice it in 4.25 years. If we go to greater distances, say for example a star that's 10 light years away, it's going to take us 10 years to notice if something happens to it or differs. If something is 100,000 light years away, it's going to take us 100,000 years to notice. Yes, Mr. Greatman.
So, sir, if there's like a potential threat, for example, if there's like this huge asteroid that is coming, I know that we might notice it when it gets closer, but then what if it's coming at a greater speed than we will envision? So, for example, an asteroid that is like at Alpha Centauri, right now coming at great speed towards us, wouldn't we be a threat or something?
And as remember, the maximum speed limit of the universe is the speed of light, and that is 300,000 kilometers per second. So if something travels towards our solar system and it emits some sort of light, electromagnetic radiation, that will travel at a speed of light or perhaps a little bit slower. So then we'll still have enough time to pick it up and detect it.
Okay, thanks, sir.
It's a pleasure. Yes, Mr. Greatman. Your hand is raised. Okay, so I see we are not many students in tonight's class, so I assume it's the computer science people that is writing a test this evening, and that, yes, Mr. Greatman.
Sir, it's me, sir.
Yes.
Sir, I just wanted to know, so what type of mathematics do you use, like, in your daily research, sir?
Oh, mathematics I use is calculus. I use that over and over and over. And I also, algebra is something you also use in my everyday life. Linear algebra is quite handy when you want to calculate simultaneous equations. Sometimes you have a lot of simultaneous equations that you need to work out. So linear algebra and then calculus. I more basically use calculus every day because I'm working with radio astronomy and I'm looking at the electromagnetic spectrum. How do you visualize an electromagnetic spectrum? How do you visualize something that's not visible to us with our naked eyes? So the easiest way to visualize it is by making use of math.
And so do you sometimes work with like pen and paper, or is it most of the time just working with software?
So most of the time it will be with software, but I would say about 40% of the time it's pen and paper because sometimes the software will do something completely wonky and you have no idea what's going on. Then you have to do the calculation by hand to make sure where the software screwed up.
And so when it comes to collaborating with like mathematicians, like when do you know that like a math problem is too hard for you and that you need help?
Mm, so it all depends on you as a person. So if you perhaps get stuck for weeks on end with something, it doesn't hurt to ask someone else's opinion and ask what does someone else think about it, or what can someone else perhaps uh, think of what we should do, or what is happening. And most usually, if you ask someone to go over something for you, two eyes is better than one because sometimes you can miss something. Uh, that's a general rule with anything you do, even if you're programming something. Two eyes is better than one, and sometimes someone will pick up something that you missed. So I'm just going to turn on my camera so you say doing things by hand. So this is basically a bit of math that I've done today. So you still do things by hand.
And so I'm sure you know of these paradoxes that usually comes up in mathematics. So like for example, the Zeno's paradox, right? Do those usually come up when you're doing your like your research?
So I'm not familiar with the Xenox paradox.
So it's basically the idea of when Archimedes has to chase down a turtle. So they put them 100 meters apart, and every time Archimedes tries to chase the turtle, obviously the turtle is going to move. But as Archimedes reaches the 100 meter mark, he rests. But then, let's say the turtle walks or runs another 50 meters, and then Archimedes does the same thing, gets to the 50 meter mark, rests, and then the turtle goes on. Basically, the paradox is, does Archimedes ever pass the turtle? Because every time he runs, he only covers half the distance.
Oh, okay, I see what you mean.
Yeah.
So it depends on what you're working with. So in my everyday life, the only paradox I stumble across weekly is the Fermi paradox. And usually, when I give a public lecture or is invited as a speaker somewhere, the Fermi paradox is always a question that pops up. So that's one I'm fairly familiar with, but other paradoxes, not so much.
Thank you, sir.
It's a pleasure. So I see we are not many students, so they are writing the computer science semester tests. So before we continue on with tonight's lecture, do you guys want to see a short 15-minute video of one of the talks of the conference I'm attending? So I'm going to share one of the talks of last night. It was, I think, Mr. Levio, this will actually tickle your fancy because it's about the imaging of black holes, and all of you will find this interesting. So just to give you a bit of background on a conference I'm attending so you'll be able to understand what the talk is about. I'm part of an international research group called CASPER. It's the Collaboration for Astronomy Signal Processing and Electronics Research. So the aim of the group is to find new ways to do radio astronomy and astronomy, in meaning to develop new mathematical and physics methods to study these objects, and also to create better electronics and technology to monitor, observe these objects. So the Event Horizon telescope was built on Casper technology, software, and mathematics. So I'm going to share my screen, and hopefully you'll find this interesting. So share application screen. Share. Can you all see the screen? Okay, just shout if you can't hear anything, if something wrong with the audio or something.
Thank you very much for inviting me to talk about our project. It's really exciting. I'll try to spend a lot of time on the instrument and then give some context on science. Of course, I am a member of the EHT, so everything I say is on behalf of our amazing collaboration, which is very diverse, and we have telescope staff and engineers and scientists working on lots of different aspects of the project. So first off, why do we care about imaging a black hole? Why is this important? So first of all, black holes are mathematical occurrences of the theory of general relativity, and they also exist as astrophysical objects, which is quite amazing. They are very extreme environments where time and space come to a halt, and physics is at its most extreme. On top of that, We believe that supermassive black holes reside in the centers of most large galaxies, and they eject these streams of matter, which we call jets. These jets pierce entire galaxies into galaxy neighborhoods, sometimes thousands of light years in length, and they're the most energetic and powerful process in our universe. But we don't really know why that happens. We think the central engine is the supermassive black hole. We think magnetic field and pressure and gas forces play a role, but we don't really understand what is the mechanism that causes these. So in order to understand, where this comes from, we need to look at the central engine, which is a supermassive black hole. We have two supermassive black holes big enough to image from Earth, the one at the center of our galaxy, Sagittarius A star, and the one in the galaxy M87. M87 you can see in the corner here. It is over here. Has a well-known jet. It is actually the first astrophysical jet ever observed by humanity. It was observed in 1918 with the Lowell Observatory in optical, and they saw this stream of matter coming from this tiny point, which is the galaxy itself. And in fact, what powers it is the supermassive black hole. So if we look up the night sky in the Virgo constellation, there is a galaxy called Virgo A, or M87, 55 million light years away from us. Because there is a lot of gas and dust between us and the center of the galaxy, we need to observe in radio waves. Although this stream of matter, this stream of plasma is visible in the optical and radio, only radio can peer all the way down to the center because it's not absorbed by gas and dust. So if we use radio waves at higher and higher frequency with larger and larger instruments to increase the resolution, we can zoom down, follow the stream of matter all the way down to its core, which is where we observe with the EHT, the black hole M87. And with the EHT, we observe at a frequency of 230 gigahertz, which is the frequency high enough so that we can peer through all the way down to the black hole. And also, it just happens to be the frequency that gives us a resolution that lets us image the shadow. Now, in order to piece together a synthesized Earth-sized instrument, we use a technique called very long baseline interferometry. So I'll explain a little bit how this works. So say we have a source very far away, so that if we are in the far field regime of radiation, because it's far away, the waves that arrive on Earth are plane waves. Because of the Earth's geometry or curvature, there is a time delay between the arrival of a specific wave at each telescope. Now, the distances between telescopes tell us information about the image. Telescopes close together tell us about information on large scales because they see a lot of signal in common. And telescopes further apart see smaller signal in common, so they see a small scale structure in the image. So by combining many different telescopes at different locations on Earth and at different distances from each other, we can piece together different directions, orientations, and scales in our image and combine them. So this time difference is, however, quite important because we want to be able to correlate the signal received at each telescope. So in order to see what signal is in common, we need to time tag our data. And we do this using atomic clocks called masers. They're hydrogen maser transitions that time tag our data with very precise time. And these clocks are so precise, they lose about a second every 100 million years. Now, once our data packets are time tagged, they're recorded onto hard disks. We essentially freeze the light received at each telescope and record them and then combine them at a later time where we can then align the signals and reconstruct an image. So the EHT project is a 10-year project. The first multi-baseline, multi-telescope observation was done in 2007. Then as we expanded the array, we've added more and more telescopes, and some telescopes got decommissioned, so we lost well. And then finally, in 2017, we made our famous observations. In 2017, we had 8 telescopes at 6 different locations, 6 single dishes, and 2 phased arrays. Now you'll notice all of these telescopes look very different from each other. This is because we did not build them. They were built for completely different science, so self-standing science. And we just happened to borrow them because they can observe at 230 gigahertz, the frequency at which we need to get to M87. And they are at high enough and dry enough places, and at the right places where we can reconstruct an image from different scales. So high and dry places, some of the most dry deserts on the planet, is extremely crucial for our observations. Because we're observing at such a high frequency, we are very susceptible to water vapor and turbulence in the atmosphere between us and space. And the Earth's atmosphere scrambles our signal and absorbs it because of the water vapor. So we really need to pick the right sites that maximize our signal. And our signal is very weak. So our black hole image has a total flux density of about 0.6 Jansky, so almost half a Jansky. And if you take into account all of the radio observations made in the history of humanity, it is less energy contained in that than a single snowflake dropping to the ground. So we're looking at really, really small signal, and it is really crucial that we build sensitivity. So building sensitivity with the EHT means increasing the recording bandwidth and frequency bandwidths. So across many years of our radio observations, we had different systems. The ones that matter the most is our current system here with the Roach 2 digital backend and the Mark 6 recorders. So our 2017 observations recorded at 32 gigabits per second. So this is following, the log of the doubling bandwidth, which is quite amazing that we're able to see this biannual doubling with our own observations and equipment. So we observed at 32 gigabits per second with 2 polarizations and 2 gigahertz basebands. So 2 polarizations because we want to make polarization maps of the magnetic field around the black hole, and I'll show a little bit of that later. Since then, we are now at 64 gigabits per second, so we've doubled our frequency bandwidth as well to make more polarization and frequency studies. So the signal we receive at the telescopes is, of course, an analog signal, and it's 230 gigahertz, so it's very high frequency. We down convert it to a 2 gigahertz baseband with block-down converters, and then we digitize it with our Roach 2 digital backend with 2-bit sampling. And then they're recorded onto our Mark 6 recorders. This is one example of one Mark 6 unit. There's 4 boxes here, which we call modules. These Mark 6s, one records at 16 gigabits per second. We need 4 Mark 6 recorders to record at 32 gigabits per second with 2 polarizations. So there's 4 modules per Mark 6, and each Mark 6 contains about, each module contains 8 helium-filled hard drives, which you can see stacked here. All our Mark 6 recorders are equipped with custom cooling for high altitude use. All our equipment needs to be heavily tested at high altitude in these kind of pressure chambers because at sites we're at least 10,000 feet above ground, sometimes 15, 16,000 feet. So we definitely do not want equipment to overheat. Also, including our equipment is not well exercised. We only observe about 2 to 3 times a year, including our dress rehearsals and practice observing. So we really need to make sure all our equipment can easily start up and not run into too many issues when we do observe. So this is what one full backend looks like. This is from Spain. And you can see here are 4 Mark 6 recorders. We have our digital backends here, our digitizers, our down converters. And for the total of our 2017 campaign, we used 92 individual modules for 736 hard drives. In total, we recorded about 3.5 petabytes of data across our 5 triggered days. So we observed for a 12-day window during our EHT campaign, 5 days to trigger for observations, and we need to keep a very close eye on the weather. As I mentioned, we have stations at very high and dry places, but that doesn't guarantee best weather all the time, especially in April, when we observe, it's kind of marginal weather everywhere. So we need to look for these pockets of good weather for half the Earth, which is really difficult and a really difficult task to coordinate. We were really lucky because in 2017 we had probably the best weather we've ever had, and I don't think we'll ever have this kind of weather again. So we keep a very close eye on current and forecasted weather and telescope operations to figure out when to trigger. So here are some nice pictures from our 2017 observations. On top of having operational local staff at the telescopes. We also send our own EHT members to the telescope. Here are some pictures of our EHT members with local staff. And they act as our local experts for back-end equipment and for the telescopes. Then once we record the data, they get shipped to our correlation facilities, these two places, MIT Keck Observatory and the Max Planck Institute for Radio Astronomy. Each facility correlates about half of the data. So at correlation, we combine the signals from each telescope, we align them, we throw away all the noise that is telescope specific, only to keep the signals seen in common between pairs of telescopes. And it takes into account the Earth's curvature and these timing effects that we may measure from our equipment. One thing that it doesn't take into account is, again, the atmosphere. And atmospheric effects, because we have this jitter in our phases in the data, it prevents long averaging. So if we average turbulent data, we end up destroying our signal instead of piling up and building signal to noise. So we need further data calibration. The advantage, though, is that we record at very high bandwidth. And so we do have the signal to noise to actually track atmospheric changes in the data. From that, we can refine corrections from correlation and remove the effects of the atmosphere. So here's an example. So this is real data from EHT. So in yellow, you can see amplitudes, and in blue, phases from 3 baselines or 3 pairs of telescopes. Now, because we expect the phases from the source to vary very slowly, these few second phases, so this is over time over 400 seconds, these few second phases changes are entirely due to the local atmosphere. And so if we look at these 3 baselines, these are 3 pairs of total of 3 stations. We can actually triangulate which changes actually happen at each station. And because ALMA is the most powerful radio astronomy observatory in the world, and it brings amazing sensitivity, the baselines to ALMA allow us to have amazing signal to noise to actually track atmospheric phases on second scales and actually remove them. So once we remove them, this is what the phases look like. So now if we average down over our entire scan over a few minutes, we build sensitivity. We don't destroy signal anymore. And this is all real data. This is really what it looks like. And it's really amazing because of our high recording bandwidth, we're able to build enough sensitivity to track and remove effects of the atmosphere and really build our data, build our signal to noise, and build confidence in our data. Now, of course, understanding the data is one step, but understanding telescopes is another. We need to understand how our telescopes work, what are their sensitivities, so that our detections, which are now at signal to noise, go into a flux density scale. So we need them in Jansky so that we can make an intensity map. So in order to do that, we need to take into account, again, the sensitivity from the atmosphere, the size of the dish, different surface, elevation effects, signal chain, noise level, and also polarization leakage. Now, I mentioned that our total intensity image was about half a Jansky. The polarization signal is even less than that, way less than that. And so polarization leakage is very important to remove because it creates a false signal in polarization, and we really need to remove it very accurately in order to make polarization maps. But there's a trick to it. So we decouple leakage and source signal using the Earth's rotation. So because we observe for such a long time, one observing track is about 8 to 9 hours, each telescope sees the source move in the arc on the sky. So the signal from the source, the real polarization signal, is expected to move over time, but the instrumental contribution from the telescope stays put on the ground. So if we combine each arc from the telescopes, we can separate those contributions. So our entire data path from the raw signals, which is 3.5 petabytes, all the way down to an image, which just can be sent on your phone, is about 12 orders of magnitude in data reduction. And the most powerful data reduction actually happens at the calibration stage. So now that we have our final data, we can start imaging. And we use, again, the Earth's rotation with a technique called aperture synthesis. So because our telescopes are at set location on Earth, as the Earth rotates, we're sampling different parts of our image. So the Earth's rotation helps us build our virtual mirror, which you can see here. So our coverage is in Fourier space. So we're sampling different frequencies in our image. So as M87 becomes visible, we get different pairs of telescopes that give us different tracks on our coverage. And as we pile these data in time and in space, we can see how our image improves. So you can see here how as we build up our data and our coverage, the image takes shape. So we imaged M87 with 3 different softwares. This one was a traditional technique for historical VLBI. These 2 were designed for EHT-specific issues, dealing with, systematics from our high sensitivity and our sparse coverage that we have. And all 3 gave very good answers. We tested all of these softwares against synthetic data where we knew the ground truth to make sure that we picked the right optimal parameters for our software, and this is the final result. So these are the 3 software images for April 11 observation, and in fact, the famous image you've seen of the black hole is simply the average of these 3. So that is the first image of a black hole. But during our 2017 campaign, we triggered 5 observing days. 4 of them had M87. So we have 4 individual observations of this ring. This one was April 11. And here are the other 3. So as you can see, over our 4 days, we don't see significant changes. Every single day gives us a ring of the same size, right on the bottom with a dark spot in the center where the black hole shadow is. In polarization, which we just released a couple of months ago, we get these beautiful images. So on top of our total intensity ring, we added the information from polarized light. You can see that polarized light only lights up the southwest part of the ring and gives us this kind of spiral structure in the polarization angles. So we get a spiral polarization structure across our 4 days, and it looks pretty similar across the days as well. I'll explain everything that we learned from this. First, we measured the size of our black hole, which was 42 microseconds on the sky, which is because we know the distance of the black hole, we were able to measure the mass, which is 6.5 billion solar masses. M87 is one of the largest and most massive black holes in our known universe. I really love this comic because it actually shows us the scale of this image. Although it's 42 microseconds, it's the size of seeing an orange on the surface of the moon with your naked eye. It is actually bigger than our solar system. So you can see the sun at the center, Pluto, the orbit of Pluto around, and Voyager 1, which is the furthest human-made object that we've sent out, just at the edge of the shadow. Now, the next step is to understand what exactly we're looking at. So we've imaged it. We know it's a ring. We know it has a shadow. What does it tell us about the physics? What are we learning? So in order to do that, we simulate a black hole and its environment. So we use fancy simulations that take into account the space-time around the black hole with general relativity and the physics around it. So we have matter orbiting, falling into the black hole, which is called the accretion disk, and it also spews out these jets of plasma, and then these disks and jets are also threaded with magnetic fields, which help push in and out material, and there's a black hole at the center. And then because of the very hot gas temperature, the gas is not atoms, it's ions and electrons. And so because we have electrons, magnetic fields, if we have very fast moving electrons spiraling around magnetic field lines, they emit synchrotron radiation that is polarized, and that is the emitted light that we observe with the EHT. So from different types of physics that we try to understand, we made a simulation library. So this is our total intensity simulation library to try to understand the signatures of a ring. There are lots of different ones here that have different gas properties, magnetic field properties, but they all have something very clearly in common. They all have a dark patch at the center and a bright ring around it. So why is that? Why did they all show the same thing? It's because this signature in our main image is a direct effect of gravitational lensing. Because we have such a strong pull from the gravity of the black hole, we have light rays from around the black hole that get bent by the gravity of the black hole, And as seen from a distant observer, if you have a lot of light rays, which is the case with the gas around the black hole, as a distant observer, you will see this kind of puffed up shadow surrounded by a ring of light, and that's exactly what we observe. Now you'll also notice that our ring of light is not smoothly uniform. It has a part that is brighter on the bottom. The reason of that is because of the inclination we're looking at. We're seeing a full ring. We're looking almost straight down the barrel of the black hole. And one side is brighter than the other because of Doppler boosting. So the side that is brighter is coming towards us, and the fainter side is going away from us. So another thing we learned from our simulations is also that the gas rotation around the black hole orbits clockwise, and that the spin of the black hole is pointing into the board, into the screen. Then we also looked at polarization simulations. So we have our polarization images. We want to understand what does the magnetic field look like and whether they actually play a role in launching this famous jet that we see in M87. So we made polarization simulations, which you can see on the left with perfect resolution, and on the right what we would see with the EHT. And we compared these polarization maps. So what it teaches us is that if you have a black hole with an accretion disk with threaded magnetic field, if you have weak magnetic fields, they would kind of look like concentric circles, the field lines. And then the synchrotron radiation that would come from these field lines would look like spokes on a wheel as seen from Earth. So we'd make polarization maps that would look like, that stick out like this, just like the animation. Now, if you have a very strong magnetic field, you will get the opposite effect. You will get spokes on a wheel, magnetic field lines, and then the synchrotron radiation would look like concentric circles as seen from Earth. So this is what our image would look like. But as you remember, our polarization image looks like a spiral, right? And so it means it's kind of in between weak and strong. So if we have a spiral structure of the magnetic field, the synchrotron radiation that we see from the black hole is also a spiral. And so we learned from this that the magnetic field strength around the black hole is about 4 to 30 Gauss, and it has a spiral structure that has a vertical component. The interesting thing about the vertical component is that it means it's able to push gas out, which means that it could be the cause and the direct link between the black hole's magnetic field and the jet launching. So that is where we stand now with EH2 results. So what's next for us? We've added new stations since then. We just observed in 2021 with the added Greenland telescope, Cape Peak telescope, and NOEMA array. We're hoping to add a telescope in Africa, but we're thinking about really long term as well, which is the next generation EHT. So with the next generation EHT, we'd like to have, because now we have the sensitivity from our large dishes, like ALMA and like NOEMA. So we'd like to put small dishes with lots and lots of different places on Earth to fill our coverage. So we're no longer sensitivity limited. And what's really cool is that say we have a simulation here of a black hole and its jet. What we would see with 2017 is just the dominating ring that we see in our images. But we know this jet exists, so we don't yet have the sensitivity and coverage to be able to image it. But with the NGHT, we'd be able to make images and link directly the ring to the jet emission from the black hole. And this will really help us understand how the jet behaves and how it connects to the black hole. And we want to extend to space. We'd like to have longer baselines, so no longer limited by the size of the Earth. We'd like to have faster orbiting in low Earth orbit to fill our coverage and go to higher frequencies even. If we have an entirely space-based array, we're no longer limited by the Earth's atmosphere, so we can go to 1 terafarad. But next generation EHT means next generation challenges. This is my final slide. Just to think about where we're going, because we're adding so many more telescopes, we need to look at our monitoring and control development. We can't just keep sending telescope experts to sites, especially if we want to observe more often. We're going to have a lot of data, so we want to expand from our 64 gigabits per second to 256 gigabits per second. We need to think about data storage and real-time correlation. For a ground-based array antenna design, we need to look at smaller dishes, which should be sufficient given the current sensitivity. For a space-based array, we're looking at whether we have a single orbiter with our ground array, which allows for quick filling, or an entirely multiple orbiter system, which allows for very slow filling but very sharp images. Then we want to build sensitivity in space. If we want a wide bandwidth and large data rates, how do we get the data down? We can't just keep hard drive there, and we can't send an airplane to get it. So we need to think about how to downlink this kind of data. And also timing in space. So our major clocks that we have at the site are the size of a mini fridge, and we can't really afford to put a mini fridge into space. So we need to think about compact solutions for timing, which is really crucial for our signal for VLBI. So I'll stop here. Thank you very much, and I'll take questions.
So what did you guys think?
So why don't they just build telescopes on the moon, considering that it has no atmosphere?
That is a solution we are investigating, but the problem there is funding. So funding will be the biggest problem putting telescopes on the moon, but that is what we are working towards.
And so
yes.
And so this woman was speaking about creating things, right? So like I kind of forgot what it was that she was referring to. So but like engineers are the people that build these things, right?
Engineers and physicists.
Okay, so does that mean like theoretical physicists have to come up with what they want before the physicists try to build the equipment?
So yes, there's one and two ways you can do it. So usually when you build or design a telescope, you build it with a specific purpose in mind to do a specific science or research. But that can't be the only goal of the telescope. If you build a telescope, for example, to only observe a certain object, then it's a waste because you can only observe that object, not any other object as well. So you build it with a main purpose to observe a certain kind of object, but you must also be able to observe other objects as well. So that's usually the design principle. The other one is you build a telescope and you see and you try and detect something with it, but it's also a waste. So it's a combination of what science do you want to do, and then how are you going to do the science, and then you construct your equipment.
And then so is that science dependent on like what you know? For example, like if you specialize in mathematics, your science would be more theoretical, and if like you're more into chemistry, like it's gonna be like a different type of science that each scientist does.
Yes, but one thing you will realize if you start going into postgrad and into industry or even remain in academia, it's a lot of interdisciplinary. So take me for example, I'm in the gray area between physics and engineering because I work on physics, I work on a theory of physics, I work on a few mathematical models of my own. But on the other side, I also help to create a few of these instrumentations. So I'm basically in the middle. So once you are out there, you find a research interest for you. What makes you tick? What is interesting for you? And then you can contribute in research. And if you don't have a skill set, then you learn the skill set.
Thank you, sir.
It's a pleasure. So, Navian, so Hawking's radiation actually exists as matter suspended by the black hole. Do black holes dissipate? If they do, that is proof existence of white holes. So yes, black holes dissipate. So right now, currently, white holes is a theory. The math is holding up, but then again, we still need to detect a white hole, and that's where the problem comes in. So that's important for our lectures further. So I don't know if you caught it in her talk, the Event Horizon telescopes, to image a black hole, it used 3.5 petabytes of data, and the black hole is 6.5 billion solar masses.
So if one of the space, like our space shuttle, got a gravitational slingshot from a black hole, so would that allow us to be able to reach other stars in like a few years, like in less than a decade?
Unfortunately not, because if you do a gravitational slingshot, you can do it around any object, and you just need to calculate what your approach angle needs to be and how much momentum you need to get. But unfortunately, that is one of the barriers we have, is our time limitation.
So even with that black hole that we took an image of, it still wouldn't be enough.
It still wouldn't be enough, because remember, if we get too close to the event horizon, we will get sucked in. So we will do a slingshot around the event horizon, and it all depends on what momentum we can be added to us. This is actually a really good question. We won't achieve anything close possible to the speed of light, but yes, we will pick up speed. But remember, we are still, the bounding factor is the speed of light.
Yes, sir.
So I have a comment: what is hindering the link between planetary science and quantum physics, particularly looking at quantum superposition, hinting existence of parallel universes? So there's nothing hindering the link between planetary science and quantum physics. Planetary scientists and quantum physicists actually work together on a few research projects. But if you look at the parallel universe or multiverse theory, the math supports it, but it comes then, it's good and well, the math supports it, but how do you actually observe it? And that's where the trick comes in. So in the talk, you also heard she talked about the R2-DBE, so the Roche 2 digital backend, and that is used to, whatever the telescope is looking at, the Roche 2 digital backend digitizes that data and processes that data. So my contribution to the research field of radio astronomy is in the Roche 2 digital backends.
So have any South African physicists or chemists ever been considered for a Nobel Prize?
Oof, that I don't know. That I haven't investigated. But a quick Google search should give you the answer. So let's continue with tonight's lecture. So last night we ended off with protostars and the birth line of stars before they reach their position on the main sequence in the HR diagram. So here is a simulation of how that actually works. So we will have a rotating gas cloud due to an incoming shock wave. Conservation of angular momentum spins the cloud faster and faster and faster, and that causes more particles to be clumped together, and that forms a protostar at the center of the rotating disk of gas and dust. So these stars Awesome, thank you, Mr. van der Berg. So we call these objects while crossing the birth line young stellar objects and protostellar disks. So observations of young stellar objects and protostellar disks introduces 3 new terms. So question, since light cannot escape the event horizon of a black hole, does that mean the pulling gravitational force of black hole pulls an acceleration greater than the speed of light? No, we cannot have an acceleration greater than the speed of light. The speed of light is our absolute maximum. So number 1, star formation regions contain types of stars so young they must have formed recently. T Tauri stars, for example, are understood to relatively low mass protostars ranging from roughly 0.5 solar masses to 2 solar masses, still in a slowly contracting pre-main sequence phase. Infrared observations reveal the complicated shapes of star-forming clouds that are strongly affected by radiation and winds from nearby massive luminous stars. The formation of massive stars may both foster and disturb the formation of lower mass siblings. In the HR diagram, newborn stars lie between the birth line and the main sequence, with just the properties you would expect of stars that have recently lost their dust cocoons. Young stars tend to have very active hot corona and chromospheres, making them prominent X-ray sources. Observations provide clues about the effects of disks of gas and dust around protostars. These disks evidently cause bipolar flows that push into surrounding ISM and produce glowing nebula called Herbig-Haro objects. Astronomers also have abundant evidence that these disks are the sites of planet formation. So another comment, and think of one of the physicists that won the prize for X-rays, was born in SA but was a US citizen, we won a prize. That could be. So here we can look at this artist's representation. So this newly formed star lies at the center of a dense disk of dusty gas that is narrow near the star and thicker further away. Although the star is hidden by the edge on dusty disk, the star illuminates the inner surface of the disk. Interactions between infalling material in the disk and magnetic fields around the spinner star are hypothesized to eject bipolar jets of gas along the axis of rotation. Indicates knots of material that have moved noticeably in 2 years. The artist's impression on the right is to help interpret what can be seen in the Hubble Space Telescope's images at left and center. The detection of these jets was one of the first pieces of evidence that substantial disks often surround protostars. Some evidence of stellar youth is more subtle. An association is a widely distributed star cluster that is not held together by its own gravity. Its stars wander away as the association ages. The constellation Orion, a known region of star formation, is filled with T Tauri stars in a T association. T Tauri stars are approximately low-mass pre-main sequence objects. OB association, fairly obviously, are extended groups of more massive O and B stars. Association of stars that are journeying away from each other as we watch are clear evidence of recent star formation. How would you go about making a star? It's simple, really. All you need is something to gather together a star's mass of interstellar medium, maybe a light-year-sized broom, and gravity will do the rest, contracting the cloud first into a protostar and then into a stable star. The structure of a star is surprisingly simple. So what keeps a star stable? If there is a single idea in stellar astronomy that can be called crucial, it is the concept of balance. Stars are held together by their own gravity, balanced by the support of the internal heat and pressure. Consider the structure of a star using the basic concepts of balance. What is meant here by structure is the variation of properties such as temperature, density, and composition, pressure and composition, between the surface of the star and its center. You can think more easily about stellar structure if you imagine that a star is divided into many concentric shells, like those in an onion. You can then focus on the temperature, pressure, and density in each shell. These helpful shells exist only in imagination. Stars do not actually have such separable layers. The weight of each layer in a star must be supported by the layers below, so close to the center. So picture a pyramid of people in a circus tent. The people in the top row do not hold up anybody else. The people in the next row down are holding up the people in the top row, and so on. In a star that is stable, the deeper layers must support the weight of all the layers above. The inside of a star is made up of gas. So the weight pressing down on the layer must be balanced by gas pressure in that layer. If the pressure is too low, the weight from above will compress and push down the layer. And if the pressure is too high, the layer will expand and lift the layers above. So what keeps a star stable? The stable balance between weight and pressure is called the principle of hydrostatic equilibrium. And this is what's meant with hydrostatic equilibrium. So we have our different imaginary layers. So here we have pressure going up and weight coming down. Pressure going up, weight coming down. So the deeper layers must support all the layers going up to the surface. Everyone's still following? Okay. So the next part is energy transport. So how does nuclear fusion fits into this? How does the star generate energy, and how does the energy be transported from the core all the way up to the surface? The surface of a star radiates light and heat into space and will quickly cool if the energy were not replaced. Because the inside of the star is hotter than the surface, energy must flow outward to the surface where it radiates away. This flow of energy through each shell determines its temperature, which, as you saw earlier, determines how much weight the shell can balance. The movement of energy from the inside to the surface of a star, this plays a crucial role in determining the star's structure. The law of energy transport says that energy must flow from hot regions to cooler regions, even by conduction, convection, or radiation. Conduction is the most familiar form of heat flow. If you hold the bowl of a spoon in a candle flame, the handle of the spoon grows warmer as heat in a form of motion among the atoms in the spoon is conducted from atom to atom up to the handle. So the three methods by which energy may be transported from the flame of the candle, as shown here, are the three modes of energy transporting within the star. So radiation and convection are much more important than conduction in the interiors of main sequence stars. So you guys are happy with these three concepts? Awesome. The transport of energy by radiation is another familiar experience. Put your hand near a candle flame and you can feel the heat. What you actually feel are infrared photons, packets of energy radiated by the flame and absorbed by your hand. Radiation is the principal means of energy transport in the interiors of most stars. Photons are absorbed and re-emitted in random directions repeatedly as energy works its way from the hot interior toward a cooler surface. The flow of energy by radiation is controlled by the opacity of the gas, its resistance to movement. Opacity in turn depends strongly on temperature. A hot gas is more transparent, less opaque. So opacity means, so let me go back one slide. So opacity, in short, it's its resistance to movement. So a gas that is really has high opacity doesn't like to move, but a gas that has a low opacity can move around more. A hot gas is more transparent, less opaque than a cool gas. If the opacity is high, radiation cannot flow through the gas easily and it breaks up like water behind a dam. When enough heat is built up, the gas begins to churn as hot gases rises upward and cool gases sinks downward. The heat-driven circulation of a fluid is called convection. The third way energy can move inside a star. So you're familiar with convection. The rising wisp of smoke above a candle flame is carried by convection. There is a common misconception that the sun's core is hot because nuclear reactions occur there. That statement reserves cause and effect. Rather, it is correct to say the sun and other stars have nuclear reactions in their cores because temperature is hot enough there. So keep that in mind. It's the other way around when you think about it. There's nuclear reactions because it's hot, it's not the other way around. You observe the sun to be stable, therefore it must have certain temperature, pressure, and density in its core. If somehow you could magically turn off the nuclear reactions in its core, then without a source of energy to replace the luminosity pouring out into space, the sun would gradually lose its internal energy and start slowly contracting again, as was true during its protostellar phase before nuclear reactions started. The CNO cycle. So this is also a good question for tests and exams. You might expect other stars to fuse hydrogen the same way the sun does, and you would be right for most stars. Some stars, however, fuse hydrogen by another process, and that makes a big difference in their structures. So look carefully at figure 9.15, we can look like at the next slide, and study the steps in the CNO cycle. During the process, 4 protons combine to make a helium nucleus. In other words, the CNO cycle is really hydrogen fusion and has the same outcome as the proton-proton chain, but it's different in important ways. Notice that carbon-12 begins the cycle and ends the cycle. So the carbon-12 nucleus is recycled over and over. Notice also that a CNO cycle includes steps in which protons, so hydrogen nuclei, combine with carbon and hydrogen nuclei. So here we can see the CNO cycle. So carbon-12 has catalyst to combine 4 hydrogen nuclei to make 1 helium nucleus plus energy. The carbon nucleus reappears at the end of the process, ready to start the cycle over. And then we have the pressure temperature thermostat in stars. Newborn stars contract and heat up until nuclear fusion begins. The energy flowing outward from the core heats the layers of gas, rises the pressure, and stops the contraction. This leads to an interesting question. How does the star manage to make just enough energy to stop contracting but not to start expanding? The key is the relationship between pressure and temperature that acts like thermostats to keep the star burning steadily. Consider what would happen if the reactions begin to produce too much energy. Normally, the nuclear reactions generate just enough energy to balance the inward pull of gravity. If the star makes slightly too much energy, the extra energy flowing out of the star would force its layers to expand slightly, lowering the central temperature and density, and slowing the nuclear reactions until the star regains stability. This star has a built-in regulator, the pressure temperature thermostat that keeps its nuclear reactions from occurring too rapidly. Then we have stellar models. The laws of stellar structure, described in general terms in the previous sections, can be written as mathematical equations. By solving those equations, astronomers can build a mathematical model of the inside of a star. If you want to build a high-quality model of a star, you would have to divide a star into about 100 concentric shells and then write down the 4 equations of stellar structure for each shell. You would then have 400 equations that would have 400 unknowns, namely the temperature, density, mass, and energy flow in each shell. Solving 400 equations simultaneously is not easy, and the first such solutions done by hand before the invention of the electronic computer took months of work. Now, a properly programmed computer can solve the equations in a few seconds and print a table of numbers that represent the conditions in each shell of the star. Such a table is a stellar model, a mathematical description of the inside of a star. So on a side note, mathematical models are important for our careers. So if you want to do an experiment, if you want to investigate something, you start with the scientific process and start out with a hypothesis that you want to test. Then you start doing investigation, and from the investigation, you construct a mathematical model. If a mathematical model is working, then you can go to a simulation and construct the simulation. If a simulation is wonky, then you go back to the mathematical model and you fine-tune your simulation. If your simulation is working, then you can go over to the experiment itself or the observation itself. If your observed data then differs from your simulation, that means then something is wrong in your mathematical model, and then you need to go back to your mathematical model again. So this is where our wonderful maths comes in. So throughout your careers, something important, and that is what I do. If someone comes to me and say they have a design of something, or they want to do this experiment or that experiment, the first question I ask is, where is your mathematical model? If you don't have a mathematical model, then you are wasting my time. But if you have a mathematical model, then we can take a look at it. Because usually when you see, I don't know, there's a lot of people in private industry that does this kind of thing. If you, for example, go on Facebook and you ask someone something stupid, and you ask someone, well, you have a house, you want a Wi-Fi mesh network and an Ethernet network in your house, and someone please design a network for your house. What most people will do is they will rock up with a bunch of repeaters and switches and cables and just start installing stuff everywhere. That's the wrong way of doing it. You first need to construct a mathematical model to calculate where you will need a repeater, a Wi-Fi router, a switch, what power would they need, what is the energy output of the repeaters, what frequency will that work, and you construct a mathematical model, and then you can go on from there. So mathematical models is very important in science and engineering. So this is our table or mathematical model of the layers of a star. So stellar model is a table of numbers that represent conditions inside a star. Such tables can be computed using 4 laws of stellar structure, shown here in equation form, including the principle of hydrostatic equilibrium and the law of energy transport. The table in this figure describes the present-day sun. So here are our 4 important equations for this stellar model. Everyone still following? Awesome. So when a contracting protostar begins to fuse hydrogen, it stops contracting and becomes a stable main sequence star. The most massive stars are so hot that they light up the remaining nearby gas and beautiful nebula as if announcing their birth. After the gas of the nebula disperses, the star begins its long, mostly uneventful life as a main sequence star. In a careful census of all stars, including white dwarfs, about 80% are main sequence stars. So what is the relation among stellar mass, luminosity, and lifetime? Observations of the temperature and luminosity of stars show that main sequence stars obey a simple rule. The more massive a star is, the more luminous it is. That rule, the mass-luminosity relation, is the consequence of the mechanisms causing the stability of main sequence stars. In fact, the mass-luminosity relation is predicted by theories of stellar structure, giving astronomers direct observational confirmation of those theories. To understand the mass-luminosity relation, recall 1, the principle of hydrostatic equilibrium, which says pressure, balance, weight. And 2, the pressure-temperature thermostat, which regulates energy production. A star that is more massive than the Sun has more weight pressing down on its interior. So the interior must have high pressure to balance that weight. That means the massive star automatic pressure-temperature thermostat must keep the gas in its interior hot and its pressure high. So since we are few people in this lecture, here is another tip for tests and exams. This is quite an important paragraph. A star less massive than the Sun has less weight on its interior, and this needs less internal pressure. Therefore, its pressure-temperature thermostat is set lower. To sum up, massive stars are more luminous because they must make more energy to support more weight. The mass-luminosity relation tells you why the main sequence must have a lower end. Lower mass objects have lower pressures and temperatures in their cores, and those with less than about 0.08 solar mass are too cool to allow hydrogen fusing, called brown dwarfs. Such objects have diameters only about the size of Jupiter, so 10 times the size of Earth, and although they are still warm for contraction, they do not generate energy on their own. So the relation among stellar objects, so here we have a small star, a brown dwarf, and a gas giant. Brown dwarfs fall deep in the gap between low-mass M stars and massive planets like Jupiter. If the form of new stellar spectral type is cooler than M, the warmer brown dwarfs fall in spectral class L and the cooler in spectral class T. Brown dwarfs would look dull reddish-orange to your eyes, hence the term brown, but they emit most of their energy in infrared, so meaning heat. Brown dwarfs are so cool that liquid and solid particles of silicates, metals, and other minerals can condense to form cloud layers in their atmospheres. Evidently, brown dwarfs have rocks for weather. So the life of main sequence star. A star in a main sequence is stable, with its gravity balanced by outflowing energy from fusing hydrogen. The balance must shift as the star consumes its fuel, so that even apparently stable main sequence stars have interiors that are slowly changing. As a main sequence star fuses its hydrogen, 4 hydrogen nuclei are converted into a single helium nuclei, and the total number of particles in its interior decreases. Each newly made helium nucleus exerts the same pressure as one hydrogen nucleus, but because there are fewer nuclei, its total pressure is less. This unbalances the gravity pressure stability, and gravity squeezes the core of the star more tightly. As the core slowly contracts, the temperature increases and the nuclear reactions run faster, releasing more energy. This additional energy flowing outward forces the outer layers to expand. As the star becomes gradually larger, it becomes more luminous, and eventually the expansion begins to cool the surface. As a result of these gradual changes in the main sequence stars, the main sequence is not a sharp line across the HR diagram, but rather a band. Stars begin their stable lives fusing hydrogen in the lower edge of the band, which is known as the zero-age main sequence. But gradual changes in luminosity and surface temperature move the stars upwards and slightly to the right. By the time they reach the upper edge of the main sequence, they have exhausted nearly all the hydrogen in their centers. Thus, you find main sequence stars positioned throughout the band at various stages of the main sequence lives. So here we can see a newborn star reaches stability with properties that places it on an HR diagram at the lower edge of the main sequence band, along the line called the zero-age main sequence. As a star converts hydrogen in its core into helium, it changes slowly away from the zero-age main sequence and across the main sequence, becoming slightly more luminous and cooler. Once a star consumes all the hydrogen in its core, it can no longer remain a stable main sequence star. More massive stars are rapidly, but less massive stars use up the hydrogen in the cores more slowly and live longer main sequence lives. So here we can see newly formed stars begin life at the lower edge of the main sequence. Stars exhaust the last of the hydrogen in their cores as they leave the main sequence. So our present sun is here on our main sequence diagram. The sun is a typical main sequence star. As it undergoes these gradual changes, Earth will suffer. When the sun began its main sequence life almost 5 billion years ago, it was only about 70% as luminous as it is now. And by the time it leaves the main sequence in another 6 billion years, the sun will have twice its present luminosity. Long before that, the rising luminosity of the sun will drastically modify Earth's climate and ultimately boil our oceans away. Life on Earth will probably not survive these changes in the sun, but we have 1 billion years or more to prepare for it. So this is just to show the spectral type, the mass, luminosity, and years on the main sequence of our different class of stars. So, reasoning with numbers. This is also a good example for tests and exams. The life expectancies of stars can be calculated. So you can estimate the amount of time a star spends on the main sequence. So its life expectancy. And we call that life expectancy tau, by estimating the amount of fuel it has and dividing by the rate at which it consumes the fuel. So tau equals fuel supply divided by rate of consumption. The amount of fuel of a star is proportional to its mass, m, and the rate at which it uses up its fuel is proportional to its luminosity, L. Its life expectancy must be proportional to m divided by L. You can simplify this equation further because, as you saw in reasoning with numbers 8.5 in the previous chapter, the luminosity of a star depends on its mass raised to the power of 3.5. You guys still remember this. So we can say tau equals m over m to the power of 3.5. So we can simplify this further by saying tau equals 1 over m to the power of 2.5. So if you express the mass in solar masses, the lifetime will be in solar lifetimes. So how long can a 4 solar mass star live? So T equals to 1 over 4 to the power 2.5. So that is 1 divided by 32. So solar models show the sun, presently 5 billion years old, will last about another 6 billion years. Thus, a solar lifetime is approximately 11 billion years old, and a 4 solar mass star will last for about. So here we can plug this in, and we can say this is 340 billion years. So you guys are happy with this? Awesome. Yes, Mr. Greatman.
So may you please explain the fuel part?
The fuel part. So, what do you mean over here? The fuel supply?
Yes, sir, the fuel supply.
Okay, so the fuel supply is dependent on its mass. So remember, when a star starts its fusion reactions, it's fusing hydrogen. So it comprises out of hydrogen. So hydrogen is its mass, but hydrogen is also the fuel. It's, you can say, because call it burning, but it's actually fusing to create helium. Does that answer your question?
Yes, sir, it does.
Awesome. And that, ladies and gentlemen, was our lecture this evening. Yes, exactly. So life expectancy, you can say it as a rocket losing mass. That's exactly it. Can we do another example? So I don't have another example prepared for this evening, but if you want more examples of specifically this problem, then I will create a few and I will post it during the week, if that is fine. Awesome. So if you have no more questions, then you are more than welcome to log off. Otherwise, I will see you all in next week's class. Remember to do your quiz before Friday at midnight.
So does the quiz also cover? Okay, I'm assuming it doesn't cover this work. So where does it end?
So the quiz ends before the work we've covered, the last lecture we did before recess.
Just after the one about the stars.
Yes, so because so lecture 8, so I'm going to stop the recording for now.